Hi, this is the part 2 video. We are going to discuss some system design. We have already discussed about the system design in part 1. I explained many concepts. So this is a second video for that, and um, so we are going to discuss about load balancing and latency, API gateway, protocols, CDN, so testing, security measures, distributed system design. So we'll discuss many things in this video. So let us discuss about the load balancing concepts. For understanding the load balance, first we need to understand what is concurrency. See, concurrency means we are dealing with the multiple task at a time, right? For example, you take a single cashier serving multiple customers by switching between them very quickly. It is a concurrency. Parallelism means like multiple cashiers serving multiple customers. So that is the main difference you need to understand. Concurrency means single process is performing multiple tasks. Parallelism means multiple process processing multiple things at a time. So you can see the diagram here. Concurrency, the multiple tasks are getting executed parallelly. You can see. So this is nothing but a concurrency. Parallelism means there are multiple process 1, process 2, P1, P2, P3, P4, P5. You can see that in image, right? So they are getting executed. Every process will take 1 minute after. So when all these process executes and completes things, the task can be completed in 1 minute, right? Imagine if you want to complete a task one after another, it may take a lot of time. It may take 6 minutes or 5 minutes of time. But you see, so when everything gets executed at a time, then we can finish everything in 5 minutes, right? Total time taking it just 5 minutes of work can be completed just in a 1 minute, right? So that is what about the concurrency. So you see here there are couple of differences. Concurrency is the task of running, managing the multiple computations at the same time, while parallelism is the task of running multiple computations simultaneously. So you can see we can take many examples when we are talking about the concurrency and these things. So all I want to say is just understand what is concurrency and parallelism here. So you want to achieve do something parallelly, right? So that is what about the concurrency. So for achieving that, we need a load balancer. Now we will discuss about the load balancer. So you see here in this diagram, there is a website and there are multiple users. They are working from computer, mobile, tablet, right? They want to access this website. So when request is coming to the website, this load balancer act as a some kind of mediator which can distribute the request to multiple servers. You can see in the background there are three servers running parallelly, and it wants to redirect the particular request to particular server. Why we need a load balancer? See, when all the requests are go to same server, let's say single server, there may be a chance that server may goes to hang, or it may not work due to the heavy load and overload, right? To avoid that issue, so we need a uh, some software, nothing but a load balancer, which is nothing but we call it as a load balancer. It works as a traffic cop routing client request across all servers, ensures that no single server bears to too many requests, which helps to improve the performance, reliability, availability of the applications. Okay, that is why we need load balancer. You can see here it was given a good example here. Without load balancer, see, there are 5 requests, and out of 5 there are 4 requests are going to server 1, and due to which it gets overloaded, right? It is a problem. And one request is going to server 4, it is a problem. So that is why we need a load balancer. When we have a load balancer, see, it is equally distributing the request to all 4 servers. See, total 5 requests are coming, and load balancer is redirecting each request to each server. That way the performance will be improved. Okay, traffic will be distributed, scalability, right? Optimization, we can achieve the optimization. We are utilizing all the resources, right, equally, parallelly. So it is happening concurrently. That is why we discussed of the concurrence and parallelism, right? That is why we require a load balancer. Okay, this is all about the load balancer. Basically, receives the incoming request and it redirects the request to the particular server, and check client server health. You see, it always sometimes check the server health. If any server is not working, then it may redirect the request to other servers. It distribute the health, handle the server failure. If server goes down or becomes unresponsive, the load balancer automatically stops sending the traffic to that server. No, it is its functionality. We can configure that in load balancer software and redirect it to other servers that are still functioning properly. So see, by spreading the traffic efficiently and using healthy server, load balancer improve the overall performance. So you can see all these are the benefits, better performance, because all the servers are getting utilized here. No server is sitting idle. Load balancer is making sure that every server is working right, without making it idle. The scalability works with auto scaling, so we can also dynamically add servers. Okay, if the load is very high, high volumes or high peaks of requests are coming, then we can add or remove the servers dynamically. Load balancer will get adjusted according to that. Okay, failure handling prevents the bottlenecks, handles the sudden spikes in traffic smoothly. Sometimes we will get heavy load, peak load. You take a Christmas season or any festival seasons. Most of the time, some websites will get heavy traffic. Many users they'll try to do the online business. That time, suddenly number of requests are coming, right? So the sudden spike will happen in the traffic. So that time load balancer generally handles that load evenly and distribute them properly. Okay, so this is about load balancer. So some challenges are there. A single point of failure in case the load balancer is down or so, then it's again a problem because traffic will be, it can disrupt the traffic flow. Okay, cost complexity. Sometimes good load balancing solutions are a little bit expensive, require also proper setup also, configurations. So you should configure the load balancer properly, right? You should be very careful when you are configuring the load balancer for complex applications. uh, so this and extra overhead SSL management, security, configuring security at the load balancer is also kind of complicated. So many but many benefits are there nowadays. Most of the distributed applications are microservice architecture. They're all using load balancer. Without load balancer, we can never imagine any system design. So keep that in mind. We also need a proper load balancing algorithm. Generally, we follow round robin algorithm, and there are many algorithms are there. I'm not going to discuss about them, but keep in mind we have many load balancing algorithms. We can see that there are. Okay, let me open this. I'll just show you how many. See, you got the static algorithms, round robin algorithm, weighted round robin algorithm, source IP hash, a dynamic least connection method, least response timing method. You can go ahead and read about these algorithms. Nothing but, I mean, the algorithm means they'll just uh, handling the request, how the request distribution will happen as per the algorithm. So that is why we need some algorithm. If you take a round robin, first it will go first process and next process, then third process, and if it reaches the end, and then again it will come back to first process. It is a round robin. In the same way, we have many other algorithms, right? We can learn about those things and all. Okay, next thing we are going to discuss about latency, throughput, and caching. Okay, what is a latency and throughput? See, latency is the time it takes for a request to travel from its point of origin to its destination and receive response. Let's say you send a request, okay, and it goes to the server, and the server processes that request, and it will provide the response back to client. So the total time, how much time it is going to take for a request that go for a request that is flow that is going to the server and coming back to the client, the total time will be called as a latency time. That is why you can see here the request time, for the request for request going to the server, it is taking 350 milliseconds. For for getting a response, it is taking 150 milliseconds. Then when we combine this 350 plus 150, okay, we have 500 milliseconds, right? If 500 milliseconds is called a latency time. So latency, how much latency it is taking for getting a response, generally we in technical terms we call it as a latency. Okay, if the latency is very high, then the performance is very problem. That is the performance problem. You're getting it right. So whenever the latency is very low, then that is a good application, because you are getting the response in within the estimated SLA time, right? So the round trip time, that is what the latency. So whenever we are designing a system, we should design a system in such a way that we make sure the latency time should be minimum, right? We should try to reduce the latency. If the latency is getting increased, then it means the application that was designed is having some performance issues, right? Next thing is throughput. Throughput means the rate at which the system process network can move data or carry out operations particular period of time, referred as throughput. Number of bits per second. See here, at what rate, okay, the system or process it is processing data or processing some operation is called generally throughput. So network throughput means see, throughput in networking is the quantity of data that can be sent via network in specific amount of time, right? In the same way, disk throughput, processing throughput, if you take in computing, especially in the context of CPUs, throughput is the number of operations completed in a unit of time. So throughput is also one of the parameter when we are defining the system design, the number of tasks completed in a given period. So how many tasks it can complete it, okay, we should have a good throughput, right? Good throughput when we are dealing with latency is the time taken for the task for single task to be completed, okay. So inversely related to the latency, higher the throughput often correspond to lower latency. You see, it is always latency is inversely proportional to the throughput. If the latency is very high, that means the throughput is very low. If the latency is very low, then that means the latency is very high, right? So what is our expectation here? The latency should be less. If the latency, our expected latency of our system so we want that as low as possible, then the throughput should be maximum, right? That means it should process many requests per second, then we call it as a good design. Okay. High-end user availability and performance. You see here, okay, you can see network latency, system latency. So we can call these latencies in many factors. So basically, I hope you understood what is latency and throughput here. We should have a good throughput and less latency. Then that will be the good design of the system. Okay. Okay, the catching in system design. I already discussed this in part one of the video. Catching is generally required, right? So we want to catch the details in some catchy database. We generally will have database and application server. When request comes to the application server, and it will call the database layer. It will fetch the data from database layer and display that data, render the data in the UI side. But the problem is, if every time the request is going to database, it may take a time. The latency may be high, right? Because the time that is going to take to travel the database and get the data back to the application server may be high. If every time the request is going to be database science, to reduce the latency of the request and response, we will use the cache database or cache server in between the application server and database server. So that way, what happens, the request, whenever the first time the request is coming, the first request will go to the cache database. If the required data is not found at a cache layer, then the request goes to database layer. So from there the data will be collected, and the data will be placed in the cache. Okay, when it is coming back to the when the request is coming back there, the data will be stored in the cache and it will be displayed in the client layer. The next time whenever the client requested for the same data, it does not need to go to the database layer. If the data is present in cache, it will fetch from there. That way it will increase the performance, it will reduce the latency. Right, it will reduce the latency. That is why we use the caching system when we are designing the system. So for better system, we should have a proper catching mechanism also. And catching also, I want to tell you one thing here. Generally, catching system we should not implement for every system. It depends again the requirement. Let's say if it is your banking application, right? If it is your banking application, you take a banking application. Generally, banks will have two kinds of data. One set of data is a customer data. Other set of data is a transactional data. Here customer data is always a static data, it cannot be changed. Let's say if the customer name is Srinivas Rao, and he is having some age, and his address is he's having some address details. They're always static. I mean, name and mobile number, Aadhaar number, mobile number, Srinivas Rao, and Aadhaar number, these are the static. Once some data is given to customer, it cannot be changed for longer time. So any data that is going to be static for longer time is called as a static data, and that kind of data we can store in a cache, right? We don't need to worry about that, because most of the static data we always put in the cache server. That way we can fetch the data. Why we only store a cache data? Because why we store only static data? Because if we take a dynamic data means the data which will change very frequently. Transaction data, you take a transaction data today, a customer Srinivas Rao may use his debit card for 120 rupees withdrawal. Okay, tomorrow he may withdraw 130 rupees. So it may change the transaction dates and timings. The data will change. You cannot put that kind of data in a cache database. The data should be fetched from the database itself. So this is a very important thing. Okay, that is why we use this catching in system design. You do understand that very clearly here. We only store the static data, not this dynamic kind of data in catching system. uh, and other thing I'm going to discuss here: API gateway, message queues, rate limiting. Okay, what is API gateway? Okay, let us discuss. Generally, API gateway we use in microservice architecture. We have cross-cutting scenarios like authentication, caching, rate limiting, monitoring. These kind of all functionalities we will actually uh, define at a API gateway, a separate service. Generally, instead of creating all these cross-cutting concern scenarios for each and every microservice, we actually create them in a separate service, single service, which will act as a API gateway. So as soon as the request comes to the API gateway, and it will authenticate it, authorize it, and it will also redirect that request to corresponding microservice. Okay, this is nothing but API gateway. You can see after rate limiting is one of the scenario. Rate limiting means at which rate the application can process the request. Okay, is nothing but a rate limiting. If you see here, rate limiting is a technique used in system to regulate how quickly a system processes or serves incoming request. At which rate, right? It limits the quantity of the frequency of the client request to prevent overload. Yeah. Sometimes if you don't define the rate limiting, if in case if any hackers or crackers, they can send many requests, right? They can overload the system, right? That will actually breach the system. That is why we have to define the limitation. So this application can process only 1,000 requests for a particular for these many seconds. So that way we can limit the number of requests processed by the system, is called as a rate limiting. So all these kinds of configurations we can define at a API gateway level. Authentication also, catching also, monitoring, health monitoring of the system. We can define everything at API gateway level. You can SSL configurations. You can define everything at API gateway. Okay. You see, so API gateway architecture we can use. Um, See, you can use in both in monolithic system architecture and microservices architecture here. In both the way you can use it. Uh, but the problem is single point of failure scenario. See benefits, you can centralized entry point. Okay, challenge is performance bottleneck, increased latency, complexity, security, scalability challenges, scalability, particularly dynamic. So many, some benefits are there, some issues are there. Centralized entry point, routing, load balancing, authentication, authorization, request response time. Performance bot, why we are calling performance bottleneck when we are dealing with the challenges, right? When managing high volumes of request, API gateway may become performance bottleneck or single point of failure. That is why single point of failure, increase latency, because we are adding a extra layer, right, between client and microservices, API actual services. So so there are some, you can see existing API gateway solutions. So Amazon API gateway, APG is also API gateway, Kong, Microsoft Azure API gateway, Apache, Spring Cloud is also providing so many API gateways. Right, you can actually utilize any API gateway you want to do that. We already discussed about rate limiting algorithm. Why do we need it? I don't want to get deeper inside of this. And communication protocols, CDN, content delivery network. So generally protocols, is it a HTTP protocol, or is it a any asynchronous protocol, right? We should define it. See, remote procedure call or synchronous messaging, asynchronous messaging. There are many. So protocol is nothing but how the communication will happen between two services. You have actually built a two REST services, the REST services or microservices, how they are going to communicate. So if you use HTTP, right, they can communicate with HTTP. Services can use RPC frameworks like gRPC to make remote procedure calls. And synchronous messaging. Some message brokers support synchronous messaging patterns, while service sends a message, awaits for response in another service. So you can say all these are uh, different communication mechanisms. So I want to discuss here asynchronous communication. Asynchronous is also part of communication where services sends a or publish a particular message into the message queue or broker, and from there another service will consume the data. So asynchronous kind of communication also required when you are building event driven architecture. Let's say you want to build event driven architecture of a system. You want to make a system event driven based architecture, and then that time you need this asynchronous communication. We generally use Kafka, RabbitMQ, or kind of softwares that are already there in the market, or you can use any other third-party messaging softwares also. Okay, domain name system DNS is generally, we know that every system should be identified by IP address. So remembering IP address for each and every system would be difficult in this large web of computer networks. So every computer or every server or every application will be uh, identified by the DNS. We will provide some DNS name and DNS based on the IP address. When the request comes based on the IP address, based on the DNS name, it can forward to the respective IP address, and that way request will be served. So it will make the it is like a address location of kind of address location system. So DNS catching, time to live, content delivery, proxies in systems. So these proxies, content delivery network, we'll discuss about content delivery network also. So as I told you, content delivery network is a kind of, see, uh, see, these are generally useful when a distributed network of servers that work together to deliver content like images, videos, static files to users fast and there. So, web application see generally help improve the performance, reliability, scalability of websites, applications, and web application by catching the content closer to user, reducing the latency. So, content delivery network means, let's say you have when user requested a content from a website without CDN, request is sent directly to the origin server where the website is located. The origin server processes the request and send back the requested content to user device. If the origin server is located far away from the user, it may result in longer loading time. See, we are in India. I am trying to access a website and whose server is located in Britain or America or China or Singapore or somewhere else. Then it will take time, right? A lot of time. When we are trying to search some website and the server is located in different countries, not in India, then that would be a problem. But imagine if the server is um, let's say we have some content delivery network system which actually I mean um, which actually stores the all these static files, images, and also when user requested a content from website with CDN, CDN identifies the user's location, routes the request to nearest edge server. The edge server which stores the cached copies of website content quickly delivered. So it's nothing but a kind of a system. Basically, it helps us to save the static content, to save the static data, and when request is coming, it basically sends that request to nearest edge server rather than actual server, original server that was located outside of India, right? That is way it can save the time. It will reduce the latency of request and response. Okay, that is why content delivery networks are very important. For example, take a Google or Amazon or any other website. When we are searching for something, they'll first look for the edge servers that are available near to India, right? If any server is available near to India, then it will get the data from there. Basically, it may not be the actual server, but it is server which is having all the static data, static content, right? Not the actual server. But what it will do, it will provide that content, and it also route the request to nearest server. So these all things we can actually place at content delivery networks, right? So you can see fast, what are the benefits? Faster content delivery, CDNs improve the load times, okay. తర్వాత you see improved website performance, scalability, redundancy, reliability. Redundancy is the content. CDNs offer redundancy by storing copies of content across multiple servers. If one server fails, another server can seamlessly take over. So content delivery, we have a public content deliveries and private content deliveries, peer-to-peer content deliveries, hybrid content delivery, push, pull. So many types of content deliveries are there. So when we are designing a system, so we should keep in mind if the server performance is a key factor, key performance indicator, then we should consider the content delivery network also when we are designing a system. This is a very important thing, okay. So forward proxy, reverse proxy, proxy generally act as a middle server between you and internet, right? When client wants to, does not want to disclose his information, he could actually have a proxy server intermediary between client and server, facilitating communication through forwarding request, right? um, Generally whenever request is coming from client to internet, so first the request goes to the proxy server. From there it will go to outside internet. So that's why the other systems or people who are on the internet may not be able to know from where the actual request is coming. So there are two types of proxies we can actually design. One is forward proxy or reverse proxy. I'll explain you. Forward proxy is nothing but hiding the client identity here. So the server or people in the internet may not be able to know the forward proxy. Reverse proxy is nothing but the server's location will be hidden here. I mean, we don't know from where the actual request is coming. So you see, forward proxy acts on behalf of the client to control access to enhance the privacy. Here, reverse proxy acts on behalf of the servers to optimize the performance, improve the security. Sits between client and internet for forward proxy. Sits between internet and server. The client is aware of the proxy, must configure it. The client is typically unaware of the proxy. Okay. The client needs to configure the device to use the proxy. If it is a forward proxy, the server proxy, the server is configured to use the reverse proxy. Okay. Bypassing the content while controlling the access, privacy, and harm. It intercepts the request from client to the internet, forwards them. For forward proxy, for reverse proxy, intercepts the request from internet and forwards to the appropriate server. You getting it right? So reverse proxy always between internet and servers. Whenever request is come going to the server from internet to the server, it will act as an intermediate proxy server. It will intercept that and process, send that request to servers. So forward proxy sits between a client and internet. So whenever request is coming from the client, and it will intercept and it send that to internet. So generally we will configure these proxies and web sockets. Okay, we need to know about that much. I'm actually explaining the key concepts in system design, not everything. So just keep in that mind. And here, unit testing and integration testing. So unit testing is nothing but you developed a component and you want to test a particular class or particular component, and you do the unit testing. Integration testing is nothing but you have a system with many components. You have application server, you have a web server, you have a database server, and you integrated everything all together, and you want to test everything by combinedly is called as integration testing. The whole system, after integration, you want to test the whole integration, how they are integrated with each other, and integration is working properly, how web layer is calling application layer, how web application layer is calling database layer. So these are all the things we actually cover in integration testing. Okay, we will test all the components in integration testing basically there. Security measures in a system design. Security measures in system design. Okay, let's get into there. So we have to take care of the security, protection against the cyber threats, data privacy. We need to take care of the data compliancy, intellectual protection. Okay, security is very important. Generally, for application level, we have authentication and authorization. We can have multi-factor authentication, biometric, single sign-on. All these kinds of securities we can actually define it. So authorization is also attribute-based access control. Authentication means making sure the identity of the person is correct or not. Authorization is the particular person is having proper access to a particular resource. I mean, authorization will verify that whether the particular person or process is having access for any resource or not. That will be determined by authorization. Data encryption is part of security. Generally, we encrypt the data whenever data is floating between client and server over the internet. It is, we have to make sure data is encrypted, because in the middle, if the data is if any data is stolen, or if any hacker, or if they try to interpret that, and it would be very difficult for them if the data is encrypted. So these are the security measures we actually take. See, if we also handle the access control, secure authentication, error handling. All this will be the network security. We will install the firewalls, right, for protection. So security, we have to take care of the security each and every level of system design, overall system design. So first you have to take care of security at your data level, at your application level, at your network level. Okay, at your client level also, if possible, if you at your client level also, you have to take the security. So yeah, physical security for the servers, that is also there. We can take the securities installing the firewalls. We can configure the IP addresses, whitelist some IP addresses and block some IP addresses. We can do that, right? Access control, role based access control is the one thing, making sure this particular role associated um, uh, systems only can access the certain data resource. Network monitoring, logging. So generally incident response, disaster recovery. Whenever some issue happened, whenever some cyber attack or data breach happened, malware infections occurred, right? So that time, generally incident will be rise to the cybersecurity team. Okay, so cybersecurity incidents, we call them cybersecurity incidents. Immediately the cybersecurity team and security team, they'll process the request, they'll resolve the request. So disaster recovery means, so it is a whenever some disaster occurred and you want to recover that system by resolving an issue. So so we have to make sure the disaster recovery, whenever something happened, we should have a data backup. We should have a redundant hardware data backup, copies of multiple copies of files or systems. Whenever something is failed, right, we should immediately revert back that to the actual we should bring back the system to online. This is called disaster recovery. Physical security is required for hardware, data protection, business continuity. You may have a data centers, you may have servers, right? Protecting the physical location of that servers and data centers is also very important. So these there are many security aspects are there at each and every level, right? And you can see SSL, you can configure SSL certificates, hypertext. I mean hypertext transfer protocol. We can actually configure the application with SSL with SSL certificates. So we have many levels of security. We should keep in mind that whenever we are designing a system, we should consider all these security measures. That is what it is mentioned here. Authentication, authorization, we already discussed it, and data backup, disaster recovery, secure software development lifecycle. All these are there. Okay, and so just remember that all these are required there. Distributed design system, distributed design. Uh, so now you can see here whenever the distributed system, let's say you want to build a distributed system, then you need to consider all these factors whenever you data consistency, fault tolerance, how scalable is the system. Okay, all these key things are very important when you are building a system here. Oh, you need to consider proper algorithms. Okay, ladder based algorithm, voting based algorithm. Whenever you are distributed, creating a distributed system, these are about the distribute. And also you need to trace the logs, and you need to have a proper tracing system, logging system, right? You have to trace the execution flow of different microservices, how the request is floating between among multiple services, and from where the request is going or coming in, coming out. All these things should be logged properly. Tomorrow if any issue occur, if any exception occurred, immediately we should be able to trace the request also, right? These are all required whenever you want to design a distributed system. Distributed tracing basically, generally we'll have two kinds of ID, generally trace ID and span ID. Okay, uh, across multiple services. You see, trace ID. I want to tell you what is the trace ID. A request always contains two IDs. One is trace ID. See, propagation. How request enters a service. The tracing context containing the trace and span ID is propagate. This ensures. Um, so generally, whenever the request coming, it will be marked with the uh, trace ID and span ID, how it is propagated, right? These details will be identified using a span ID. By using these IDs, we can identify any root cause of the error or exception. We can also see the visualization of those, how the request is navigated or propagated among multiple services. We can also see that there. So end-to-end visibility will be there. Okay, that would be very useful for us whenever we want to do that. Mm. Next thing is software cost estimation and performance optimization techniques. So cost estimation is also part of system design. You need to estimate and you need to build a system, uh, keeping in mind the cost of the budget of the company. Otherwise, it will be a problem if the cost is going to be very high. If your design is resulting a very costly approach, the client will not show interest to go for that approach. So you should give a flexible and cost effective system design when you are building a system. Okay, so this is all about system design and all. We already discussed about all these concepts: low level design, high level design, design principles are there. So there are some design principles, solid design principle, die principles. You can see about that. Design patterns also there. Whenever you want to build any system, you should follow all these design patterns. I told you these design patterns are nothing but are the process or approach how we design a particular system components. Okay, so this is very important. And thank you for listening this session, and thank you all, thank you very much.